Folks, Mr. Sonnenberg here. Today we're going to be talking about is keeping heat at home. Some of the stuff you might actually know about already, things like R value and also maybe like the functions. You might have learned about this in for the vacuum bottle or what we'd know as the thermos in grade 7, but R value referring to the insulative value of your home. I don't know how many of you maybe have been a part of the process of your parents building a home, or maybe in your summer jobs, you work construction and you've dealt with insulation and such in R value. I know myself, I had built a home and I built an energy efficient home, and with that home came a big understanding of the R value and the importance to keeping heat in your home and keeping heat transfer from occurring so that you can keep your house cool and you can also keep it hot in the winter. So uh, basically an overview of what we're going to talk about is R values, some materials and the R values associated with those materials. A little example of how to calculate what materials might present you with the greatest R value, and then also just a little overview about keeping warm, and then a little a little discussion about the vacuum bottle, which the vacuum bottle is directly connected to similar processes that keep our house warm. Same concepts apply when we're dealing with vacuum bottles, and there will be an actual project in this topic on vacuum bottles. So, moving on to insulation. So if you take a look at the pink insulation on the top, okay, that's your basic fiberglass insulation. So with insulation, it comes with an R value, and that R value is just a measure of essentially the insulative value that that material has. So it measures how well the insulating material slows heat transfer. The materials with high R values are better. So the greater the R value, the better it's going to be. So if you have an R value, excuse me, sorry, I don't have much of a voice right now. If you have an R value, for example, of 2.42 and you have an R value of 7.50, the greater of the R values is going to be that is 7.50, because it's a higher number. So if I wanted to increase the R value of the original material, then I would have to increase the layers of it and the amount of millimeters that I apply. And by doing that, then I can times that number by 2, do it again, I can times that number by 2, and then eventually I can increase my R value. I know with my house, what I did was, one thing I did for insulative value was, well, we went up with styrofoam block, and the styrofoam and the concrete provides a good R value. But then also what happened was I used acrylic stucco on the outside as opposed to regular cement stucco or siding, and what that did was I had to apply a 2-inch styrofoam layer around the whole exterior of the house. Then I had to scratch coat that and base coat that, so that gave me additional R value. And also I used R50 insulation in my attic as opposed to the typical R40 insulation, the blow-in insulation. So I had an increased depth. So really I just increased the amount of millimeters of the depth, and that increased my R value by 10 R values. And so the house was energy efficient for several reasons, but one of them was the insulative values. So also the materials are better insulators. So they again, they slow heat transfer, they prevent the transfer of heat and such. And so the lower the R value, the lower the insulative value or purpose. So realistically, if it has a low R value, it's not going to insulate as well, and therefore it's going to allow more heat transfer. An insulation of R12 loses heat faster than an insulation of R16. So a little example, just knowing that the higher the R value, the greater the insulation, the slower the heat transfer. So therefore it's going to hold more heat in, and it's also going to allow, in say the winter, it's going to hold heat in, and in the summer it's going to slow heat from transferring through to your house, and it's going to keep your house cooler. So just some substances, or sorry, materials, not substances, some materials here that you can look at in this data table that are going to be helpful when doing the post assessment. So what we have is the thickness of insulating materials. Also, we have the approximate R value of the materials. So the first one that we'll talk about is 25 millimeter of airspace in the cavity. So that R value is 2.04. Then 25 millimeters of airspace with reflective surfaces on the inside of the wall cavity. So using reflective surfaces also helps to reflect away heat, because heat also can be transferred in the form of light. So the more we reflect away, the less energy that or heat that's absorbed, and we can prevent heat transfer by doing so. And so that would be at 5.54, which is a decent R value. 25 millimeter of expanded polystyrene, okay, and that's going to be 3.96 R value. 25 millimeters of rigid urethane foam, 7.5. So therefore, 7.5 would have the highest R value on this chart. 25 millimeters of fiberglass, just 4.25. 25 millimeters solid wood, 1.25. 25 millimeters of wood shavings would be 2.42. And then 25 millimeters clay brick, 0.11. 25 millimeters of concrete would be 0.19. One thickness of glass is 1.0. And then thermal glass, which is two thicknesses with airspace in between, is when we have windows. So you might have heard of single pane, double pane, triple pane. In my house, I know I had triple pane. So what happens is that in the windows themselves, they have a pane of glass, an airspace, and in that airspace is air and what we have, what's called argon. And then there's also another pane, and then another space with airspace and argon, and then another pane of glass. And typically what happens now with windows is you can get them glazed. And when you get them glazed, it's almost like a tint, and it prevents heat transfer as well. So those triple pane windows, which actually surprised me because the cost of them was not nearly as high as I thought. I thought they would be extensively more or exponentially more, but realistically what they were is a few $1,000s more for the whole house just to go from double pane to triple pane, and it increased my R value significantly. So make sure you understand that there are spaces between the glass when we get more panes of glass, and that actually increases the R value. But what happens with things like wood shavings is, well, wood shavings are going to actually have air spaces in between them, and that they're going to serve as insulators. Okay. So an example, the walls in your home have 25 millimeters of expanded polystyrene and 25 millimeters of rigid urethane foam. What's the R value of the insulation? So the first thing we need to do is we have to look back at our chart and we have to check the R value of 25 millimeter expanded polystyrene. And that's actually going to be 3.96. Then we have to check the R value of the 25 millimeter of rigid urethane foam, and that was 7.50. So really what we're going to do to total up our total R value of the two materials, so we're going to add those two numbers together, and we're going to come up with an R value of R 11.46. So that's going to be our R value is 11.46 there. Okay, so if you have to calculate this, then you're just going to do so. Say for example, if we had a calculation where it said, okay, well, 25 millimeters of rigid urethane foam has an R value of 7.5. Well, what's the R value of 50 millimeter rigid urethane foam? Well, you're going to take that R value and you're going to times it by 2. So then your R value is going to be R15. Okay, so if you want to increase the insulation and limit the heat transfer, what you need to do is you need to add more insulation. So what are ways to keep, oh, and I have a little spelling mistake there, glazed. It's supposed to be glazed, sorry. Ways to keep the heat in your home. Well, you could fill the wall cavity with insulation. So make sure all your wall cavities have insulation, and that's going to prevent the transfer of heat. So this stops basically convection currents. And remember, convection currents are going to turn inwards towards each other. Okay, taking hot air and cool air and transferring, and hot air rises and cool air is typically going to fall, so this is going to circulate and cycle, and so that's going to create heat transfer. So we want to stop those convection currents. We can use double or triple glazed windows with air spaces, and then between the glass contains air and argon, and those are great for insulating. So just like I talked about earlier with the windows in my house, they were triple pane with glaze and argon air spaces, really good insulators, and they really prevented the heat transfer, and they also really help with noise as well. Didn't hear a lot of noise. Of course, I was out on an acreage, and on that acreage there's not a ton of noise to begin with, but there also were farmers in the field around and you couldn't hear much. So good for insulating, good for sound purposes as well. And then you can use doors with cavities filled with insulation. I know my doors were metal doors, except for my front door was a was a fiberglass door, but in those doors they had insulation on the inside, so they were hollow doors, but then filled with insulation. So again, helping to prevent heat transfer, thus keeping heat in the winter and keeping heat out in the summer to help my house stay cool. So what I talked about earlier was the vacuum bottle, saying that this is going to be a project, and you're probably going. And what we'll do is we'll set up a project where you have to create a vacuum bottle. So if you take a look at the diagram just over here, okay, within that diagram you have a plastic stopper at the top. See if I can just draw this here. Okay, ooh, come on. All right. So you have a plastic stopper right there. Okay. Then what you have is air trapped here, and any time that air traps, it acts as an insulator. We'll have a hot liquid inside, but if you take a look down here, what happens is we create a vacuum right here because we have double walls of glass bottles. So within that, we're going to create that vacuum inside. We're going to create that insulation and that airspace. We have an outer casing that's going to hold the whole structure together and keep allow or prevent heat from transferring. And then what happens is right here, if you take a look, oops, I just crossed that off, sorry. We have a thin silvered walls of glass. And so silvered is going to create that reflective or properties that's going to prevent the transfer of heat. If they were dark and not reflective, then they're going to absorb heat, and then that heat is, or that absorption of the heat is actually going to take away from the heat of the liquid inside. And then what we have at the bottom here is a cork to hold the flask in place. So inside these thermoses, this is basically an inner of what it's going to look like inside a structure such as that. Okay, so noticing and knowing the whole purpose of a thermos is you can keep hot and cold liquids, or sorry, you can keep hot and cold liquids, you can keep them hot or cold, you can put food, beverage in there, whatever you need to do. But that insulative concept is one that's actually going to keep those liquids in that state or in that temperature for a long duration of time. Now, the concept of the vacuum bottle, actually, those properties are used in homes as well to insulate. So it's interesting to know. And then lastly, just a little description of the vacuum bottle. So a vacuum bottle uses several of the same technologies that your house uses to warm in order to keep food and beverages warm. So it's very similar to the properties of a house and insulating a house. So inside the double glass jar, one jar is fitted inside the other, similar to the windows in the double pane. So they'll have those air spaces that creates extra insulation. Some air is removed from between the two jars, and that is where the name comes from. The space is a partial vacuum. So we create a vacuum seal. Okay, and also good for insulation. The jars are painted with silver reflective coating. Again, reflective purposes, it's going to prevent the transfer of heat. And then rubber or plastic keeps the glass away from the outer case. And then the cap is also insulated, so it's filled with insulation so that heat isn't lost through the cap as well. So you're going to have to actually make one of these vacuum bottles, so you might want to take a look at the diagrams and such, and in the activity I'll run you through it, no problem. Okay, so that's everything I had about keeping heat in the home. Hopefully this stuff helps you to answer questions in your post-assessment. Okay, thanks guys. Bye.